I will start. So we're talking about morphisms. So that if x and y are varieties, then a map phi from x to y is a morphism, sometimes also called regular map. If first phi is continuous, this image of subset is closed, and the second is that the pullback of a regular function on open subset is regular. So for f for say U subset, an open subset in the target, and f regular on open subset, we have that the pullback of f, which is just defined as the composition with f, is regular on the inverse image. We had seen how this works for affine algebraic sets and affine varieties, and then we had looked at the projective case. And I had said that these are the morphisms to projective varieties are given by equivalence classes of, say, n+1 tuples if we are in Pn of rational functions. And then last I was looking at the special case, which are the simplest cases of morphisms between projective varieties. So these were polynomial maps. Simplest case of morphisms between projective varieties. This is just if x in n is closed, subvariety, and we have some polynomials, m, which are in the coordinates of this first projective space, of this homogeneous of the same degree. Then the map, which I can denote f0 to fm from x to m. I forgot something. So with no common zeros on x, so with, if I take x intersected the zero set of these polynomials, this is empty. Then this map, which just sends p to the point with homogeneous coordinates f0 of p until fm of p, is also a morphism. This is because I can look at the locus where one of these are not zero, then I divide every one by them, and then it's given by a tuple of rational functions. And the assumptions I made here make sure that that the assumptions that we had for morphisms given by rational functions are satisfied. I wanted to give a couple of examples of this. So we had, for instance, can look at this map from P1 to Pn, which sends a point with homogeneous coordinates A0, A1 So, all the monomials of degree n in some order in A0 and A1. So I have A0 to the n, A0 to the n minus 1, 1, A0 to the n minus 2, 1 squared, and so on until A1 to the n. So this is obviously a polynomial map, namely phi can be written obviously in terms of the coordinates of projective space. It's just if the coordinates on P1 are x0 and x1, it's just given by x0 to the n, x0 to the n minus 1, x1, and so on until x1 to the n. So it's a polynomial map. And thus a morphism, because obviously these have no common zeros on P1. And one can easily see what the image is. A closed subset, which I can call Cn. So this is the zero set of, so I first write it down, so y0, y2 minus y1 squared, y0, y3 minus y1, y2, and so on, y0, yn minus y1, yn minus 1. Take the zero set of these polynomials in. So why would this be the image? Because here we can see, so certainly the points here lie in the image. If I take the zeroth coordinate and multiply it by the second, I get the square of this. And you can easily see that all these are satisfied. All these relations are satisfied. And you can also rather easily see that you can reconstruct this A0 until A0, A1 from this. So in fact, so this is it's a closed subvariety. It's irreducible because it's the image of this P1, which is irreducible under a morphism. And if you know that if you have something irreducible and you have a morphism to somewhere, the image must be irreducible, because if you had two closed subsets whose union is not the whole of whose union is the whole of this thing, but none of them is equal to it, you can take their pre-images, and they are now two closed subsets of the source of the map, whose union is the whole source, and but none of them is equal to it, so it would show that the source is reducible. So it's a trivial argument which shows that the image of something irreducible under the morphism is always irreducible. So, and I claim this map is an isomorphism. Because I can give the inverse map. It's just very simple. It's just a projection to the first two factors, y0, y1, from P1. So once you're in the image, so this y0, y1 for an image point would be y0 to the n, y0 to the n minus 1, a1, which is equivalent to So it would be A0 to the n, A0 to the n minus 1 A1, which is equivalent to A0 A1, which is what you started with. You can work this out in detail and see this is the inverse, and so they are isomorphic. So this Cn is called a rational normal curve of degree n. It does occur sometimes in life because it's kind of a special example of a curve with special properties. So what one actually finds is that this thing does not lie in any linear subspace of Pn, but only in the whole of Pn. And it's the curve which has the smallest possible degree with this property. Anyway, but we don't. Let me just see. Important was there. Okay, that's not important. Okay, one simpler example of polynomial maps are just a projective change of coordinates, in some sense just linear maps from Pn to itself. So this is the next example. So we take some matrix A, n plus 1 times n plus 1 matrix, A0, 0 until A0n, an0 until an, so an n times 1, n plus 1 times n plus 1 matrix with coefficients in K. So then, okay, this obviously, and I want this to be invertible. So the rank is n plus 1. So then we can define a map where we denote A brackets from Pn to itself, so morphism, which just takes a vector, which I maybe now write it like this, so B0 to n, and I send it to the matrix applied to the vector where now I write it vertically. And if I want, I should again make it a row vector. So let me write it like this. So I take here the corresponding, so maybe I do this, make this a row vector, and then take the class of projective space. So this is called a projective change of coordinates. And now, I claim this is a morphism because I can write it like this. How is it? So if I look at this matrix, I have here B0 to Bn. So then the image point will be A00, B0, A01, B1, and so on. And so that means as a map, it's just the following. I have A00, x0 plus A01, x1 plus A0n, xn, and then it goes on with the other coordinates, and we have A n0, x0 plus A n xn. So this is the map written out in coordinates, and you see it's a polynomial map. It's given by polynomials of degree 1, which is obvious because it's a linear map. So this is a polynomial map. the fact that the matrix has maximum rank will imply that these polynomials have no common zero in Pn. And so this is a well-defined polynomial map defined on the whole of Pn. And you can also see that this is an isomorphism because it's obvious what the inverse of A should be. There should be the corresponding morphism which is given by the inverse. Because if I take the inverse of this projective change of coordinates, this is actually just what we get if we apply this to the inverse. So one can actually show, so the only isomorphisms from Pn to Pn are the projective change of coordinates. On the other hand, you could also say that these are somehow the trivial isomorphisms of this thing to itself. They could just given by linear maps of the, Pn is a n plus 1 minus the origin divided by this equivalence relation, and it comes from a linear map from a n plus 1 to a n plus 1. So for many purposes, one would want to consider two things to be essentially equal if they are related by a projective change of coordinates. But anyway, these are the only isomorphisms from a projective space to a projective space of the same dimension. In fact, yeah, okay, I think it's even, okay. So this is this, maybe one other example, which is, projection from a point. So assume we have x in the n plus 1, say in Pn. Closed subvariety with such that, say, a certain point is non it, which is not in it. So with such that the point 0, 0 with 1, that this point is not in X. Then one can do what is called projection from X. So maybe I call this point P. Projection from P is just the morphism given by, if the coordinates on Pn are x0 to xn, it's just the map x0 to xn minus 1, so just the projection on the first n minus 1 coordinates from x to n minus 1. So if X does not contain this point, we can do this projection from it. And in fact, you can really actually see that what happens is that you have, if this is X, and you want to view the point here, this is our point P, and you can view this if you view this Pn minus 1 as the locus in Pn where the nth coordinate xn is 0. You can really view this as a projection like this, that you look at the line to this point, and when it hits this, it's mapped to the intersection point with this. So okay, and so you get picture, and then there will be some image like this. And these kind of projections are used often, because if you have some variety in a high dimensional projective space, maybe it's useful to have it in a smaller space where you can control it better. And so if you have certain assumptions, just by projecting from a point, you can achieve that the map to the image will be an isomorphism, and so you can put it into smaller projective spaces, and then maybe you can work with it better. But we will not. I just mentioned this. Okay, so this was what for the moment I wanted to say about these morphisms. Now the next thing we will want to talk about is products, which is in some sense just another way to look at morphisms, or I mean at least it's very related to it. So you want to look at products of varieties, and there's some products. So it's just, for instance, if P from X to Y is a morphism, then you could look at the graph set of all P of P in X is a, under nice assumptions, will maybe be a subvariety at least is a subset of X times Y. And it can be many properties, for instance, of the morphism can best be studied in terms of the product. We'll find out that under suitable assumptions it will be a subvariety of the product, and then one can study that. And there are also other things that you can best do with the product. So you want to be able to talk about the product of varieties. And then this helps you to, some properties of morphisms or also of varieties can best be expressed in terms of products. We'll later see there's a notion which is called that a variety is separable, which replaces, I mean, obviously in algebraic geometry the varieties are not Hausdorff, but this is what replaces for us the Hausdorff property. And this can be expressed in terms of the product, namely that the product in X, that in the product X times X, the diagonal is closed. And there are other such things. So we want to be able to talk about products. So this is very easy for affine varieties and not quite as easy for projective varieties. So we start with the affine case. And here is not very much to see. So it's just the product of a variety X in AN and Y in AM is just X times Y, which lies in AN plus M. So definition, let X in AN, Y in AM be affine varieties. So here, I mean, really closed subvarieties of the n, the m. The product is just the usual product. X is x times y, which is, you know, just what it usually is. It's just a set of all points p, q in so an times am, which is our just an plus m, such that p is in x and q is in y. Okay, so the product is naturally just a subset of this bigger affine space. Now we want to first see that if these are affine varieties, so if these are closed subsets, this will be closed, and if these are both irreducible, then this will be irreducible. So denote x1 to xn, the coordinates on the first factor an, and y1 to ym, the coordinates on the second factor a to the m. Then we can write, because x is closed in an, we can write this as a zero set of some polynomials. So x is the zero set of f1 to f whatever L, where the fi are some polynomials in the first set of vector variables. And in the same way, y will be the zero set of some polynomials in the second set of variables, y1 to ym. And then what does it mean that this point, that the first n coordinates, so that we lie in the product means that the first n coordinates lie in x and the last m coordinates lie in y. So therefore it follows that x times y will just be the zero set of the self-same polynomials but now in an plus m. No, just the first n coordinates are supposed to fill the fi conditions, and the last m coordinates are these. This is just a product, so this is a closed subset in an plus m. So the product of two affine algebraic sets is an affine algebraic set. And now we would like that if these are varieties, then it will also be irreducible. Slightly less obvious. So if x and y are both irreducible, then x times y is also irreducible. Now, we will obviously later also want to deal with the projective case, so we want to do the argument in such a way that it also works in the projective case, so therefore we again do this with a topological argument. And this is the statement that we prove is the following lemma. So let x and y be two irreducible topological spaces. We give a topology, well, it's okay, cases. So assume that x times y has a topology such that the following holds. So for all points p in x and q in y, we have the inclusion maps of p times y into it and q times x into x. So we have the inclusions. So how do I want to note it? So say jp from y to x times y, which sends a point, say a, b in y to p comma b. And we also have the map iq from x to x times y, which sends a point a in x to a comma q. So, and what I want is that these, for all p in x and all q in y, these are continuous. I don't know how I wrote this, continuous. Then x times y is irreducible. So it's a slightly strange condition. So we have two irreducible topological spaces, and we require of the topology of the product only that these inclusions here are all continuous. Then the product has to be irreducible. And then obviously, in order to show that the product of affine varieties is irreducible, we have to show that these assumptions here are satisfied. Okay, let's try to prove this lemma. In some sense, a simple okay, so obviously we make an indirect argument. So we assume that x times y is reducible. So we assume that x times y can be written as the union of two closed subsets S1 and S2, none of which is equal to the product. So Si is strictly contained in x times y, and they are also both closed for I equals 1 and 2. And we will want to deduce that either x or y must be also reducible. And so we will write down the candidates of two closed subsets of x, which should decompose it into closed subsets. So for 1, 2, I equals 1, 2, we put pi to be the following. We take the points, all points p in x, such that if I take p times y, so the whole fiber over p, everything whose first component is p, is contained in Si. Okay? So first, we want to see that these Ti are closed. I claim that Ti is equal to the intersection over all q in y of iq to the minus 1 of Si. Why is that? So what does it mean? I want that, so IQ is the map which sends A to AQ. So I want that for all possible values of Q, it's in the inverse image of the set where, okay. So this IQ to the minus 1 of Si is just, so IQ is just the map which sends A to AQ. Now, if I take this intersection of all of them, and I have to lend, so iq to the minus 1 of Si is just the set of all p and x, so that p, that the point pq lies in Si. But now if I make the intersection, it means that pq must lie in Si for all q, which is in Y, so which is the same as p times Y must lie in Si. Okay, and so this is an inverse image of a closed subset by a continuous map, so it's closed. And we have an intersection of closed subsets, so this is closed. Okay. And now we want to show that X is the union of these two sets. So we use again this argument I already used once before as JQ so I should say this IQ to the minus 1 of Si is closed itself because it's the inverse image of a closed subset under a continuous map. And so it's closed. And then we take this intersection of closed subsets, and there it's closed. So SJQ is also, so I've used here that the IQs are continuous. Now we have to use that the JP are continuous. SJP is continuous, and Y is irreducible, we have that the image of JP is also irreducible. So JP of Y, which is just P times Y, is irreducible. And now it should be clear that this will work because as it's irreducible and the union of the SIs is equal to the whole of X times Y, it must be contained in one of the SIs. So, thus, the SI are closed and the union is X times Y. So by irreducibility, we have that P times Y is contained in S1, or P times Y is contained in S2 for all P in X. But this just means that the union of T1 and T2 is equal to X. So now we have written X as a union of two closed subsets, and obviously none of them is equal to X because none of the SI is equal to X times Y. And Ti is strictly contained in X because by definition of Ti, if Ti is equal to X, it follows that Si is equal to X times Y. And so it follows that X is reducible. And so as we are assuming that X is irreducible, it follows that X times Y had to be irreducible. In particular, for our affine varieties, we get that x in AN, y in AM, affine varieties, then x times y in AN plus n is an affine variety. No, they are irreducible. So, why is that? We have to check the assumptions of this lemma. So we have to see that these inclusions that I had there are indeed continuous, and they are continuous because they are morphisms. So we have to check. So if I take a point Q in Y, I can give it coordinates, say B1 to Bm, point in Y. Then what is the map IQ? So the map IQ that I had defined before, from x to x times y, is just the map, was the map which sends a point A in x to A, comma Q. What does it mean? The first coordinates are sent to themselves, and here we just put Q, the coordinates of Q. So that means to send it to itself. So if I put here the coordinates to be x1 to xn, then this just means that IQ is given by x1 to xn, and the last coordinates are b1 to bm. So these are the coordinates, so therefore they are regular functions, and these are constants, namely these coordinates of these points, therefore they are also regular functions. So IQ is given by a tuple of regular functions, so it's a morphism. And thus continuous. And obviously I can do the same with the other inclusion of y. So in the same way, I have jp from y to x times y, which sends a point say b to p comma b is a morphism, and therefore continuous. So now the lemma applies, and we get our result. Okay, so this proves this. So now we want to show, in some sense, the basic property of the product of varieties. In the case of affine varieties, it's somehow a general thing that you can do this in a very general setting, for categories or something. If you have some objects in a category, you can define the product, and it's something which satisfies a certain universal property. And so in this case, the universal property tells us what are the morphisms to the product in terms of the morphisms to the two factors. And I will want to first show you this for affine varieties, and later we will also have to show it for projective varieties once we have defined their product. And in some sense, this universal property is what makes the product the product. Because in some sense, things are determined by how they behave under morphisms. And so if I know the morphisms to the product, in some sense, I know everything that there is to know about the product. And so here in this case, so we have the universal property. In this case, it's something very simple, and it's also very easy to prove. So proposition so first, so let x and y and am find varieties. The first statement looks pretty trivial and also is. If I take the two projections from x times y to the two factors, these are morphisms. So P1 from x times y to x, so A, comma B maps A, and P2 from x times y to y, A, comma B maps to B are morphisms. Okay, so this is in some sense the trivial part, and the second is that in terms of these, we can say what it is. So what are the morphisms into x times y? So let z be any variety. So first, the morphisms from z to x times y are given by pairs of morphisms, one to x and one to y. So are precisely the maps which I could call FG from x from z to x times y, which sends any point P to f of P, G of P, for f and g, f from z to x, and g from z to y. Morphisms. So I've now written it in this way. Maybe I can just, more standard way of writing such a way is the following. So equivalently, a map P from z to x times y is a morphism if and only if the first projection with phi and the second projection with phi are morphisms. You can see, because you can see that if you take this phi and then you make the projection to the first factor, this will be f. If you take this phi and make the projection to the second factor, this will be g. But anyway, I just write it. You can, if it's not obvious to you, you can check as an exercise that this is indeed equivalent. So let me try to prove this. The first statement is in some sense entirely obvious because we can write, we are in here a fine space, the n and the m, and obviously we can write the projections in terms of the coordinates. So let x1 to xn, the coordinates on n, and y1 to ym, the coordinates on am, on the second factor, then P1, the projection to the first vector, is just given by the coordinates x1 to xn. So therefore, it's a polynomial. It's given by regular functions. You could also say it's a polynomial map of affine varieties. And in the same way, P2 will just be y1 to ym are morphisms. Okay, so this is, in some sense, obvious. Now, the second statement. I mean, obviously, there are two things to see: that these maps are all morphisms, and that all such maps are morphisms. One of these directions is kind of trivial, namely that these are all morphisms. So let's take a morphism at H from some variety Z to X times Y. Be a morphism. So then I can just compose this with a projection to X and to Y. So let F to be P1 composed with H and G to be P2 composed with H. Then what does our H do to a point P? So then for P in Z, we have H of P. Obviously, it has a part in X and one in Y, which is it's just a pair of the points, the first projection of P and the second projection of H of P, and the second projection of H of P. No, it lies in X times Y, and its first component is the first projection, the second component is the second projection, so this is just F of P, P of P. It's given in this form, and obviously, as H is a morphism and the Pi are morphisms, these are F and G are morphisms as compositions of morphisms. Okay, so this shows one direction. Every morphism is of this form. Now, let's take a map of this form. So, conversely, let F from Z to X and G from Z Y be morphisms. Now we are in a fine space here. To be a morphism means it's given by here an n tuple of regular functions, here an m tuple of regular functions. So then F is equal to F1 n, and G is given by G1 to Gm, where the Fi and the Gj are all regular functions on the whole of Z. Now, we know that morphisms to a fine space or to subvarieties of a fine space are given by functions which are regular, by tuples of functions which are regular on the whole of the source. So then, obviously, this map Fg is just given by all of these. And so it's given by an n plus m tuple of regular functions. Okay. So isomorphism. Okay. Okay, so that was as much as I wanted to say about the find case. Now we come to the projective case, which, I mean, the product in the projective case, which is a little bit more difficult. The problem is that if you just take the product, say, Pn times Pm, this is not obviously a projective variety. No, it's not a subset of some projective space. So if we want to, we only know how to deal with projective or affine varieties. So we somehow have to make this into a projective variety. Well, okay, we do this by finding a map, an injective map from the product Pn times Pm into some larger projective space such that the image is an irreducible closed subset, and that we will identify with the product. So let me first tell you about this embedding, the Sega embedding. As I said, so we want to study the product of projective varieties. But if I take, for instance, the product Pn times Pm, this is not somehow a subset of any projective space. So we cannot really view this as so it's not directly a projective variety. And so what we'll do is we give an injective map from Pn times Pm into some projective space Pn. We will see later what this n is, with image a closed subvariety. And then we will identify n times Pm with this image, which thus becomes a projective variety. And if we have instead the product of two projective varieties, x and Pn and Pm, I can take the image there, and it still, of those, it still works. So now the real thing one has to do is find this embedding, this map. So let me now define this Sega embedding. So this n, this big N that we have here is actually as follows. So let n to be small n plus 1 times m plus 1 minus 1. So this is the space in which we want to embed it. So let x0 to xn be the coordinates on our first p small n, y0 to ym the coordinates on the second factor Pm. And as you see here, the number of homogeneous coordinates on P large N is as many as the product of the number of coordinates here and the number of coordinates here. So we put, so we want to number the coordinates on the P large N as follows. So let Zij for I from 0 to N and J from 0 to M be the coordinates on P large N. And you can see this is the correct number. These are n plus 1 times m plus 1 homogeneous coordinates. So the projective space has dimension, is Pn, where n is n plus 1 plus m plus 1 minus 1. Because we have always one more homogeneous coordinate than what the projective space is, number of the projective space. So now we want to define this map, which are called sigma from Pn times Pn, so P large M. And so you see a coordinate here, a homogeneous coordinate, corresponds to a pair, one coordinate from here and one coordinate from there. So what we can do is we just take all the products of one coordinate here and one coordinate here. So what I mean is, if I have the point A0 to AN in P small n and the point B0 to PM in PM, I just sent it to all products of the coordinates of these points. One coordinate from here, one from here. So the ijth coordinate of the image, so this was a large N obviously, is AI times Bj. So this is I times Bj, where I goes from 0 to n, and j goes from 0 to n. So this is the map. And I denote large sigma, the image. First, maybe we should make sure this map is actually well defined, but that's basically trivial. So sigma is well defined. Because we have, so if we take other representatives, we get the same result. So sigma of lambda A0, so lambda AN, mu B0 to mu BM. So if I multiply here all the coordinates by lambda, here by mu, lambda mu out 0, this is just lambda times mu times AI times Bj, where I and j runs through the same thing as before. And obviously this is still a non-zero element in K, so this is just as a point in projective space IA times Bj. Okay, so lambda is well defined. Now, I want to show that, not lambda, sigma is well defined, this Sege embedding. Now I want to show that it's indeed injective and that the image is a closed subset of Pn times Pm. So, following proposition, sigma is injective. So, this is maybe first. And the second is that sigma, so the image, closed in large N. And in fact, I can say, expect exactly what the equations are. I can write sigma is equal to the zero set of the following equations. So I take Zij, Zl. No, remember the coordinates on P large N were given by such pairs of numbers, minus Zil, Zj, where I and j runs to all possibilities. I and k from 0 to n, and j and l from m. Okay? So this is all the zero set of a large number of polynomials, homogeneous polynomials of degree 2 in these coordinates. Okay, so let's prove this. First, the injectivity is rather simple. So assume 2 points, two pairs of points are mapped to the same. So if, so sigma of A0 to AN, B0 to BM is equal to sigma of another such pair of points, so A0 prime to AN prime, B0 prime to BM prime. Assume we have that. So that means by definition that the set of all the products, so that it means that the tuple AI Bj is equal, this point in projective space is equal to the set with the same thing with prime. So these are points in projective space, so there must be some lambda so that all the AI prime Bj prime are obtained from the AI Bj by multiplying by lambda, by the same lambda. So then there exists lambda, non-zero element in K, such that, which way did I want it? AI prime Bj prime is equal to lambda AI Bj for all I and j. So the same lambda does it for all. Well, this is a point in projective space, so there will be, so B0 to Bm is a point in projective space, so one of the coordinates will be non-zero, so we choose such a coordinate. So choose 0 such that, which one did I want? Bj0 prime is not 0. No, this one is not the 0 vector, so one of the coordinates will be non-zero. So then I can take here the second one to be J0 and bring everything on the other side, so obtain that AI prime is equal to lambda times Bj0 divided by Bj0 prime times AI. No, I've just taken this equation with j equals J0 and brought it on the other side. But this means, and this is still true for all I, but this is some non-zero constant, and so it means So this thus it means thus A1, A0 prime to AN prime is equal to A0 to AN as a point in projective space. Now obviously we can do the same way when we interchange the role of A and B. So in the same way, we get that B0 prime to Bm prime is equal to B0 to Bm. So thus the map is injective. Okay, so this was the first part. And now the second part. So we want to show that the image of this map is precisely this closed subset here. So obviously two parts of it. One thing is that sigma maps Pn times Pm into large sigma. And the second is that you get everything in this way, so that every point in sigma lies in the image. So the first part is very easy. So let W be this above zero set. So I define W to be this whole thing. So I say clearly sigma is contained in W. Why is that? If we are in the image, what do we have? We have the AIs. So if we are in the image, we have that the ijth coordinate is AI times bj for AI, the A vector in Pn and B a vector in Pn. So if we have this, so therefore if we are in the image, what is written there is just this equation is just, we want that AI bj times AK L should be equal to AI L times AK bj. And this is trivial because, multiplication is commutative. So this is obvious. And so for a point in the image, these relations are obviously fulfilled. So now we have to show that the map is, that the image is precisely that. So small sigma maps Pn times Pn surjectively onto this set here. Okay, and so we have to take a point in this W, and we have to show it lies in the image. So let Aij, I from 0 to n, j from 0 to m, be in the image. So be not in the image, in this zero set. We have to show it's in the image. So let's just choose some indices KL with AKL is not 0. We are in projective space, so certainly we have a non-zero, this is a non-zero vector in, a class in projective space corresponds to a non-zero vector, so one of the coordinates has to be non-zero. We choose a coordinate which is non-zero. Now, we can obviously do the following. if I take our vector aij, so where I and j still run from 0 to n and 0 to m, I can multiply it by this non-zero constant, and it's the same. No, I've done nothing. I've just multiplied everything, every coordinate, with the same constant. So this is the same point in projective space. But now I can apply the relation. Aij times akl is the same as ail times akj. So this is the same as, maybe I still write it here. So this is I goes from 0 to n, j goes from 0 to m. So this is the same as ail times akj, I from 0 to n, j from 0 to m. But now you can see, here we have the index I runs over all the coordinates one has all the coordinates one has in Pn. Here the index j runs over all the coordinates one has in Pm. So this is just equal to sigma of ail, where I runs from 0 to n, and akj, where j runs from 0 to m. So therefore it lies in the image of this map sigma. So this relation somehow allows us to make this thing into a product by multiplying just by a constant, but then splitting it up like this. Okay. So this was that. So we have defined this map. So sigma, so this map is called the Säge embedding, and the image is called the Säge variety. Sigma from Pn m n called Säge embedding. And image sigma in Pn is called the Säge variety. Obviously, all after the Italian mathematician Beniamino Säge, who I don't know whether he was at the beginning of the last, I think, of the 20th century. Okay. Now, I'm a bit slower. Now, in the case, so for Pn, we have this cover by these open subsets Ui, which are isomorphic to An. And we want to show that we have something similar here, which will allow us to, to study things also locally. So note, if we take this set sigma in Pn, this is covered by the affine open subsets which I maybe call sigma ij, which is just sigma intersected, which maybe I call it uij, where uij is just the open subset of Pn, where the ijth coordinate is, is non-zero. So I should maybe, just to be sure that you're not confused, I write Uij like this without a comma, but you maybe should think a comma. It's not the product I times j. It has two indices, I and j. No, and all the time before, ai and so on, this is always two indices. So Uij is the set of all points A, KL, such that Aij is not zero. And so we take the points such that the ijth coordinate is non-zero. By definition, if we are in the image, the ij's coordinate is the product of the ith coordinate in Pn and the jth coordinate in Pm. So therefore, this is the same. We have that sigma ij is equal to sigma of ui times uj, where ui is equal to the set of all a0 to an in Pn such that ai is different from 0, and uj, by a little bit of abuse of notation, is the set of all points in Pm, P0 to Pm, such that Pj is non-zero. And as the ijth coordinate in the image is the product of these, that this is non-zero means that both of them must be non-zero. So therefore, by definition, this is this. And we know that we have this map ui from an to ui, which just puts in the ith place 1, and uj from am to ui, we know are isomorphisms. Okay. So now I want to just see that all these things are somehow compatible in the following sense. It's the following proposition. If I take this map sigma, I compose it with the product of the maps small ui times uj. So this is a map from an times am to sigma ij. So we send a pair of points pq, n and q and am. We send it to first to ui of p and j of p of q. These are all small u's, so these are this is in big ui and this is in big uj, and then we apply sigma to it. And the claim is that this is an isomorphism. That means, we'll see that we have this open cover of sigma by open subsets which are isomorphic to an times am. So an plus m, as it should be if this thing for Pn times Pm. So now we want to prove this. So we can assume that I is equal to j is equal to 0. I mean, the numbering really plays no role. We just may have a slightly easier life if we don't have to worry. So we put I and j equal to 0. So then what do we get? If we apply the sigma composed with ui times uj, we apply this to a point in an times am. So first coordinates a1 to an, b0 to bm, b1 to bm. What is it? First, we apply ui, which adds a 1 in the 0th position, and similarly here. So this is the point in projective space, sigma applied to 1, a1 to an, 1, b1 to bm. And now sigma is you take all possible products. So this will be somehow some vector in the projective space P large n. So it's Cij, I from 0 to n, j from 0 to m. And what is this? How does one compute it? Well, we have to just, so we have with C00 is equal to 1, because it's 1 times 1. Ci0 is equal to ai for I bigger than 1. C0j is equal to bj for j bigger equal to 1. And if both are positive, we just have the product. So Cij is equal to ai times bj for I and j both bigger equal to 1. So we can see that this is a morphism because it's given by regular functions. I can write it explicitly. So we can write explicitly that this is that the coordinates of this are functions which are regular everywhere, and as so I can write this explicitly as sigma composed with ui times uj is given by some regular functions fij with f00 is equal to 1, fi0 is equal in the same way equal to the ith coordinate xi on an, f0j is equal to yj, and fij is equal to xi times yj. So they are all given, therefore, by regular functions on an times am because they're given by polynomials. They are regular everywhere, as you can see, and they don't have a common 0 because one of them is 1. And so it's a morphism. Okay. And now we want to show it's an isomorphism. So I can just write down what the inverse morphism is. I just say, in terms of the coordinates on this projective space Pn, I can just write it down as z10 divided by z00 until z n0 divided by z0, 0. 1 divided by z0, 0. M divided by z0, 0. So these are all regular functions on the sigma ij, because the ijth coordinate, the 0, 0 coordinate is non-zero there on sigma 0, 0, because that's precisely what one has. So the denominator is not 0. So these are regular functions. And you can easily see that if you start with a1 to an, b1 to bm, and you first apply this map, and then you do this, it gives you back what you had, and also the other round. So this is the inverse morphism. Okay, and so they are isomorphic. And then I just will say what this means for us. So in future, identify n times pm with this image sigma in n, so via q is identified with sigma of pq. So then this last proposition, which we had here, says with this identification, this identification therefore identifies sigma ij with large ui times uj. So last proposition then says that Pn times Pm is covered by the open subsets Ui times Uj with isomorphisms Ui times Uj from An times Am to Ui times Uj, and the corresponding inverse I times phi j from Ui times Uj. Okay. So that means that somehow this is somehow obviously as one would expect. Pn has an open cover by these Ui's, Pm has an open cover by this Uj, and now Pn times Pm has an open cover by the Ui times Uj. And the Ui's are isomorphic to An, the Uj's are isomorphic to Am, and the Ui times Uj are isomorphic to An plus M. So basically, therefore, this proposition says that somehow this embedding gives the right structure of projective variety to the product so that this thing that we obviously want holds. Okay, let me stop here. I will we meet each again on Wednesday. If there are there any questions? Otherwise, I wish you a good evening. and we see each other on Wednesday.
Thank you.